Okay, section 4 from chapter 11 on lines and planes in space. So first we're going to be looking at the parametric equations of a line in space. It says that a line L parallel to the vector V located at ABC and passes through the point P, x1, y1, z1 is represented by the parametric equations. So basically a parametric equation, if you remember from previous, is that it are separate equations that have a variable t. So most of the time the t represents time or an angle. So you're looking at the separate variables of a function with respect to some other variable. So x equals x1 plus at, y equals y1 plus bt, z equals z1 plus ct. x1, y1, and z1 are the points that are on the plane, and a, b, c are the components of the vector that are parallel to the plane. Once you have the parametric equations, you can rearrange those three equations and solve for t, and you have the symmetric equations of a line. And we'll see how to do that in example 1. Next is the standard equation of a plane in space. So a plane contains the point x1, y1, z1, and has the normal vector in, ABC, can be represented by this function. So a times x minus x1, b times y minus y1, c times z minus z1. Again, a, b, and c are the vector that's on the plane. x1, y1, and z1 are a point that's on the plane. Once you plug into standard equation of a plane, then you can distribute and collect like terms, and that is the general equation of a plane. The angle between two planes is a familiar formula. Cosine theta equals the absolute value of the two normal vectors that are in the plane, n1 dotted with n2, divided by the magnitude of n times the magnitude of n2. Also, two planes are perpendicular to each other if the two vectors on those planes have the dot product equal to 0. And they are parallel if the two vectors are scalar multiples of each other. Also, I can find the distance between a plane and a point using this formula. D equals the absolute value of vector PQ dotted with n, so that's a point and a plane, over the magnitude of vector n. And we'll see an example of that in a little bit. So example 1 says to find a parametric equation and a symmetric equation through the point P that is parallel to vector V. So to do that, like I said earlier, it's the equation equals the point plus the vector times t. So in this case, x is going to equal 2 plus 2t, y will equal negative 3 minus 3t, and z will equal 5 plus 1t. So the first number after the equal sign is part of the ordered triple, 2, negative 3, 5. The next number that's multiplied times t is part of the vector 2, negative 3, 1. So these are the parametric equations for this plane. Now we're going to rearrange each equation and solve for t. So for x equals 2 minus 2t, I'm going to subtract 2 and then divide by 2. So t will equal x minus 2 over 2. Same thing for y. I'm going to add 3 and divide by negative 3, so that t equals y plus 3 over negative 3. Z minus 5 will equal 1t, so then z minus 5 divided by 1 equals t. Now since dividing by 1 doesn't change the value, if you don't want to put the divided by 1, that's fine. So since all three of these equations equal t, then we can substitute one for the other and create what are symmetric equations. So x minus 2 over 2 equals y minus 3 over negative 3 equals z minus 5 over 1. So these are the symmetric equations for this plane. Okay, example 2 is saying the same thing. We have a point 0, 1, 0, and we already have three parametric equations for a plane that is parallel to this one. So what I'm going to do is, since I know that the point, the 5, 7, negative 2, is another point that's on that plane, I'm going to replace 5, 7, negative 2 with the point on the plane that I want. So 0, 1, 0. So x will equal 0 plus 2t, y will equal 1 minus 3t, and z will equal 0 plus 1t. So all I did was replace the 5, 7, negative 2 with 0, 1, 0. Now I'm going to solve each equation for t. So x equals 2t, and then divide by 2, so t equals x over 2. Y minus 1 equals negative 3t, so y minus 1 divided by negative 3 equals t. Z equals 1t, which is the same as z divided by 1 equals t, or just t equals z. Same thing here, all three equations equal t, so I can substitute one for the other, and these are the symmetric equations. Okay, number 3, same question. This time we are given 2 points. So I'm going to take the original point, 3, 1, 2, and then I need a vector that I'm going to create out of the other 2 points by doing terminal minus initial. So if I do negative 1 minus 3, 1 minus 1, 5 minus 2, that gives me the vector negative 4, 0, 3. Then I have the same process. I'm going to write my parametric equations and then solve for the symmetric equation. So x is going to equal 3 minus 4t. Y is going to equal 1 plus 0t. Z will equal 2 plus 3t. So those are my parametric equations. Now I'm going to rearrange and solve each one for t. So x minus 3 equals negative 4t. That means t equals x minus 3 over negative 4. Y minus 1 equals 0. So I'm going to leave that y minus 1 equals 0. Z minus 2 equals 3t, which makes z minus 2 divided by 3 equal to t. Now in the previous 2 examples, all 3 equations equaled t. I could substitute them for each other, which would be the symmetric equation. Since all 3 do not equal t in this case, y minus 1 equals 0 and not t, then there are no symmetric equations for this situation. Okay, number 4 wants us to find the general form of the equation of the plane. So for the equation of a plane, we need a point and a vector that is on the plane. So we're going to plug into this formula, a times x minus x1 plus b times y minus y1 plus c times z minus z1. So your point is going to be x1, y1, z1, and your vector is going to be a, b, c. So we're going to plug those in where they belong. So negative 2 times x minus 5 plus 1 times y minus 6 minus 2 times z minus 3 equals 0. So this is standard form. Just plugging it in is standard form. When I distribute and collect like terms, that will be getting it into general form. So distributing, I'll get negative 2x plus 10 plus y minus 6 minus 2z plus 6 equals 0. Then when I collect like terms, negative 2x plus y minus 2z plus 10 equals 0. So this is the general form of the equation of this plane. Okay, number 5 is the same question, but this time they give us 3 points that are on the plane. So from those 3 points, I'm going to create 2 vectors, vector AB and vector BC. Now these are just 2 vectors that are somewhere on this plane. I need what's called a normal vector. So the normal vector you get by doing the cross product of these 2 vectors like we did last week. So the cross product of AB and BC, remember you cover up the first row and first column, and you do 1 times negative 2 minus negative 5 times 4, and then I. Then I'm going to cover up the middle column And that's going to be 1 times negative 2 minus negative 2 times 4j. And then last, cover up the last column, 1 times negative 5 minus 2 times, or a negative 2 times 1. So then we're going to simplify in our parenthesis here. Negative 2 minus a negative 20 will be 18i. And I have minus a negative 2 plus 8 will be negative 6j. And then negative 5 minus a negative 2 will be minus 3k. So here's my vector, 18, negative 6, negative 3. I'm going to use this vector and the point A to create the equation of the plane. So remember, your vector is ABC that we're plugging in, and your point is x1, y1, z1. So when I plug into the formula, I'm going to have 18 times x minus 2 minus 6 times y minus 3 minus 3 times z minus a negative 2 equals 0. Then we're going to distribute. So that's going to be 18x minus 36 minus 6y plus 18 minus 3z minus 6. When I collect like terms, 18x minus 6y minus 3z minus 24 equals 0 is the general form of the equation of the plane. Okay, number 6 wants us to determine if the planes are parallel, orthogonal, or neither. So from the problem that we did earlier, when we plug in the vector and the point into that general equation, the numbers that are in front of the x, y, and z, or the coefficient of x, y, and z, were the coordinates or the components of the vector. So we're going to take those out of these two planes, then determine if they're parallel, orthogonal, or neither. So for this first plane, the vector 2, 0, negative 1. So it's 2x plus 0y minus 1z. Same thing for the next one. So the second vector will be 4, 1, 8. So now to determine if the planes are parallel, orthogonal, or neither, we're going to start with parallel. Remember, they are parallel if they are scalar multiples of each other. So if I do 2 divided by 4, I want to see, is that equal to 0 divided by 1 and negative 1 divided by 8? Since those are not equal, then these planes are not parallel. So now we're going to see if they are orthogonal to each other. If they are orthogonal, then the dot product will equal 0. So if I do the dot product between these two vectors, I want to see 2 times 4 plus 0 times 1 plus negative 1 times 8. So that's going to give me 8 plus 0 plus negative 8, which does equal 0. So since the dot product is equal to 0, then the planes are orthogonal. Okay, number 7, we want to find the angle between the planes. Here's our formula. Cosine theta equals u dotted with v over the magnitude of u times the magnitude of v. So we need the two vectors that are in these planes. We're going to take the coefficients of each of those variables. So our first vector is 3, negative 4, 5, and our second vector is 1, 1, negative 1. So we need to do the dot product of the two vectors, so u dotted with v. So 3 times 1, negative 4 times 1, and 5 times negative 5, or 5 times negative 1. So when I add those together, I get negative 6. We're going to do the magnitude of u, which will be the square root of 3 squared plus negative 4 squared plus 5 squared. So that's going to be the square root of 9 plus 16 plus 25. Which is the square root of 50. And I don't need to simplify this radical because I'm going to plug it into a formula in a second. The magnitude of v is going to be the square root of 1 squared plus 1 squared plus negative 1 squared. So that's going to wind up being the square root of 3. So we're going to take these three pieces and plug them into the formula. Cosine theta equals the absolute value of negative 6 over square root of 50 times square root of 3. So in your calculator, you're going to do inverse cosine, make sure you're in degree mode, of 6 divided by the square root of 50 times the square root of 3. So we'll get that the angle between these two vectors is 60.7, or not these vectors, it is the vector, but the angle between the planes is 60.7 degrees. Okay, so example 8, we're going to find the distance between the point and the plane. So we have a point 4, -2, -2, and a plane 2x minus y plus z equals 4. So point P is a point that is not on the plane. I need point Q, a point that is on the plane. So what I'm going to do is I could plug in any numbers I wanted for x, y's, and z's as long as I get an ordered triple that satisfies this equation. So what I did is I plugged in 0 for z and 0 for y and then solved x. So when z and y equal 0, then x has to equal 2. So the point 2, 0, 0 is going to be my point Q that is on this plane. Okay, now I need the vector n that is on this plane, and remember the vector that's on a plane are the coefficients of the variables. So vector n is going to be 2, -1, 1. So to find the distance between the point and the plane, we're going to find the vector PQ. So I'm going to do my Q's minus my P's. That'll give me the vector PQ is -2, 2, 2. And then we're going to use the dot product of PQ with n. So when I do the dot product of vector PQ and n, we're going to do -2 times 2 plus 2 times -1 plus 2 times 1. So when I add all of that up, that equals -4. Then I need to find the magnitude of vector n, so the square root of 2 squared plus -1 squared plus 1 squared, which when simplified equals the square root of 6. So to find the distance between the point and the plane, then we're going to take the absolute value of their dot product, which was -4. The absolute value will be +4, and I divide by the square root of 6. So this turns out to be approximately 1.63, and we would go ahead and put units. Oh, sorry.